This video clip deals both with the polar and the highland climate types. Interestingly, Vladimir Köppen's original climate classification system just included these first 5 climate groups, up through polar climates. The highland group is something that's added with our modified Köppen system that we're using in this textbook. Let's start with the polar climates. There's 2 polar climates represented on this map as pink and purple, and not unexpectedly, they tend to be near the poles. So where do we find polar climates? Near the poles, in the polar regions. Think of Antarctica, Greenland, northern Canada, and northern parts of Scandinavia and Russia. Their characteristics, well, you can imagine, enduring cold, long cold winters, and short, cool summers due to the extreme high latitude. The sun angles are low throughout the year. In the winter time, the day lengths are very, very short. Combined with the low sun angle, it's going to make for very cold days. And then in the summertime, even though they have very long days, the sun angle is still very low in the sky, resulting in very little insolation. In polar climates, no month has an average temperature greater than 50 degrees Fahrenheit. These are the lowest temperatures in the world. Also, polar climates are very dry. People tend to imagine them being wet with snow and such. But actually, they're very dry. They get very little precipitation because, first of all, there's not a lot of liquid moisture present because of the cold temperatures, and thus very little evaporation. Also, though, remember our pressure zones. The polar high, of course, is a high pressure. And high pressure, we tend to have descending air. And for precipitation, we need clouds, and that results from rising air. So polar climates tend to have very little moisture present and also no mechanism for uplift. We divide the polar climates into 2 subtypes based on their summer temperatures. You can see that we're not using the typical codes that we use for the second and third letter for polar climates. Indeed, we don't bother with a code for precipitation as it's not that important or distinctive. Rather, the second letter that we use here is for summer temperature, and we're not using the typical A, B, C, D. Rather, we're just referring to tundra or frozen. And we'll elaborate on this on the next few slides. So here's a summary of our discussion thus far on polar climates. Pause the video and read through this carefully. Tundra is located around the Arctic in Canada, Scandinavia, and Russia, as well as on Greenland, and even a little bit fringing on parts of Antarctica, though that's not shown here. Notably, with climate change, we're going to start seeing more tundra in some of these locations as polar ice caps melt. In the tundra, there's 1 to 4 months above freezing. You can see that on the climograph. If you get to where freezing is, somewhere around 32 Fahrenheit, 0 C, you can see 1 to 4 months are above freezing. So liquid water is available for plant growth, and indeed, you do have low-lying plants. Tundra, in fact, is named after the vegetation, these low-growing plants. No trees are present, but you do have grasses and forbs and other low-lying plants. Notice the extreme temperature differences from winter to summer, though not as extreme as the subarctic climate that we looked at earlier. Also, high pressure dominates in this region because of the polar high. So there's no rising air and very little rainfall as a result. Most of the precipitation that does comes in the summer due to convective uplift because of the warmer temperatures. So you can see very little rainfall, though not considered a desert because the precipitation needs are so low as well. Here's another shot of Alaska showing tundra, and as well as another climograph from Greenland showing a tundra climograph. Again, low-lying plants, but no trees are present. Now we can contrast the tundra climate with the ice cap climate, or the EF climates shown here. These occur in Greenland and Antarctica, basically at high latitudes in the continental interiors. It encompasses about 9% of the world's land area, though as you know from climate change, this number is decreasing. In the polar ice cap climate, all average monthly temperatures are below freezing. Thus, vegetation cannot grow, and you have a permanent cover of ice and snow. You can see two climagraphs shown here. Again, note that both of them, all the monthly temperatures are below freezing. Freezing would be up here somewhere. It's off the chart, actually, on both graphs. And then you can notice which of these do you think is a southern hemisphere climograph and which is a northern hemisphere climograph. Just to remind ourselves that in the northern hemisphere we see warmer temperatures in June, July, August, and in the southern hemisphere those warmer temperatures would be in December, January, and February. Interestingly and distressingly, our polar climates are rapidly changing. Our ice caps are melting. This figure here from your textbook shows the average minimum amount of ice sheet present in the Arctic in the summertime versus what was present in 2012, which was particularly warm summer. But even so, the amount of sea ice in the Arctic is diminishing rapidly, and it won't be long before the Arctic will be completely open of sea ice. As you can imagine, that will put some creatures at high risk, and it already has for polar bears, which rely on the sea ice for hunting and traveling. Also, not just the sea ice is melting, but also the polar ice cap on Greenland and Antarctica is also melting much faster than we anticipated. And as a result, we have rising sea levels. And every coastal community in the world, including ours, needs to be dealing with that, and many of them are dealing with that. We certainly are here. You may not consider yourself a coastal community, but we're on the bay, and the bay is rising as well. Preparing for rising sea levels in the United States is trillions of dollars investment. Florida, of course, is most at risk, and you can look at city websites for the coastal cities in Florida, Miami in particular, and see what a fix they're in terms of they're actually raising the streets right now in Miami. Lots of money, taxpayer money, used to combat this effect of climate change. Another rather distressing impact of climate change is that the tundra is melting as well. This is a summer photo, so you don't really get the feel of the fact that it's generally frozen. But remember, tundra only has temperatures above freezing 1 to 4 months of the year, so most of the year it's frozen. And even in the summertime, you wouldn't have to dig very deep, perhaps just a foot or a few feet deep to find frozen what's called permafrost. So there's material here in the tundra that never thaws during the year. However, as our climate changes and warms due to global warming, the tundra is melting and the permafrost is melting. And the result is that there's a lot of methane that has been trapped for centuries or more in the tundra that is now escaping. Methane is formed due to anaerobic, without oxygen, decomposition that has occurred in this area because it's largely been frozen. As that methane escapes, methane's a greenhouse gas, and it's only going to drive warming further. Additionally, you don't even have to think about methane, but to think about all this organic material here that's frozen much of the year is now not as frozen, and you have rapid decomposition occurring by soil bacteria, which puts out an enormous amount of carbon dioxide. Just like you and I exhale CO2, so too do soil bacteria. And so we have huge outputs of CO2 that can be expected. And again, CO2 is a greenhouse gas, so this will further accentuate climate change. So both methane and CO2 releases from the tundra are starting a positive feedback loop that it's not even clear if we will be able to reverse at all. Scary stuff. Here's table 8.6 from your textbook that gives you a summary of the tundra and ice cap polar climates. Additionally, as usual, I encourage you to pause the video and read through these learning check questions to make sure that you're understanding the material. The last of our major climate groups is the highland climate. Notably, this climate group is controlled primarily by elevation. As such, there are really few generalizations that can be made about this climate as a group. There are a wide variety of conditions that could exist, and they may change dramatically over a very small distance if elevation gain is significant. For example, along the equator, you would expect A climates. But in the highland regions of Africa, you can likely find C, D, and E climates as you go up the windward side of the mountains, and then B climates as you go down into the rain shadows. You would expect a similar pattern in equatorial regions here near the Andes. Indeed, in some of the highest mountains, you have tundra near the top, or even ice cap when you have glacial ice. So elevation trumps all for these highland climates, and you can have any wide variety of climate types in any place in the world just solely based on the elevation. In our own region, consider the Sierras, or further east, consider the Rockies. At the top of these mountains, it's tundra-like, but yet they're in a mild mid-latitude or severe mid-latitude climate. You can see that visually as you go up the mountain and you run out of trees. You get to what's called the tree line, after which you have virtually tundra-like vegetation present, as there's not enough moisture and the temperatures are too cold to support a long growing season, and there's less trees. Your textbook has an example that's quite local to us. Consider Sacramento, Placerville, and Twin Lakes. 3 cities at about the same latitude, but very different altitudes, right? And you can see the effect of temperature basically going down as you go up in elevation. And you can also see how precipitation goes up as you go up in elevation on the windward side of the Sierras. So elevation can play a crucial role, and we often just characterize these kind of mixed up climates as highland climates, as they don't seem to match the other climate areas in their region. All right, we made it through an entire discussion of the 6 major climate groups and all the different climate subtypes. Your textbook concludes this discussion of climate classification with a diagram showing the idealized distribution of climates on a hypothetical continent that straddled the equator. See if you can talk your way through the pattern. Pause the video now and really check out this diagram. Seriously, pause the video and check out this diagram until it makes some good sense to you. And then check out another visual model showing much the same thing. This is from a previous version of your textbook. I kind of like it, and it shows much the same thing. Pause the video and check this out. And then notice that Africa, more or less, follows this pattern as well. Our A climates near the equator, especially the tropical wet climates right at the equator, tropical savannas around them, perhaps some monsoon areas if the continental conditions are just right. Then we have around 30 degrees north and south, we have some deserts. Further north, around 35 on the western margins, we have the Mediterranean climate. On the eastern margin, we have the humid subtropical. We run out of continent here on Africa before we get to the marine west coast, but you can go up here and see that in northern Europe, the marine west coast, and then the more severe mid-latitude climates here. I think both of these idealized global pattern diagrams are quite instructive, and I encourage you to review them again. Alrighty, you made it through our entire discussion of global climate types. Next, I will post one more video that will help you work your way through this week's climate classification assignment. You'll be using a flowchart to determine climate types of specific weather stations. It's kind of fun.